So here's some help with figuring this out. Please read through all the directions before you listen to all of this, otherwise it probably won't make a whole lot of sense. Every living thing is composed of carbon atoms, and how carbon then binds to other types of atoms determines the chemical structure of living things. And when you see something that's drawn like this, every one of those kinks or those ends represents a carbon. So in this case, there would be 4 carbons on there. If we drew an object that looked like this, which looks like a hexagon, each one of these kinks, once again, would represent a carbon. So there's 6 on there. If there's nothing there, you just assume it's a carbon. So if we look, for instance, down below here, for this example, with dichlorobenzene, we'll see that there are 1, 2, 3, 4, 5, 6 carbons. This ring right here in the dibromobenzene, similarly, even though you got that kind of circle inside, it just represents there's resonance, meaning that the double bonds are rapidly moving through it and alternating. Those also represent 6 different carbons in there, and same thing with the menthol. So whenever you see something where you see just something sticking out, it's an end, it's a kink, you assume there's a carbon on it. Now, carbon is very versatile because it can have up to 4 different bonds. Whether that means it's bonded to 4 hydrogen, making methane, that, or if it's just bonded to 3 things, double bonded oxygen, hydrogen, and another hydrogen, or if it's actually triple bonded, right, to something like oxygen to make carbon dioxide. The point is that it has the ability to bind to a bunch of different kinds of things, and you can go up to 4 bonds. So assuming we're looking for 4 bonds all the time around the carbon, let me go ahead and erase this. And to determine how many hydrogens are on the carbon, if there's nothing bonded around the carbon, it's just seen as this, like for instance something like that, you can assume that that's carbons and then hydrogens bonded to those carbons. So in this structure right here, we see that there are 1, 2, 3, 4, 5 carbons, and then there's hydrogens all around it. So that's 1 bond, 2, 3, 4 around that. That carbon's already bonded to 2, so it's 1, 2, 3, 4. This carbon is 2 bonded around it. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So what you end up is 1, 2, 3, 4, 5. C5. In this case, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens. The one on the right side, we'll see 1, 2, 3, 4. 2, 3, 4, 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds. And so in this case we have a C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, H10. Oops. H10. Where you see some things that are a little bit more complicated, like the dichlorobenzene on the bottom, you see there's double bonds. So you see these carbons already have some extra bonds on them. So if you see in the case of, for instance, these hydrogens on the bottom here, these carbons on the bottom, this carbon connected to the chlorine is bonded 1 here, 2 bonds, 3 bonds, 4 bonds. So that chlorine can't have that carbon can't have any more bonded to it. This the one up above it is also a carbon that's connected to chlorine, single bonded to another carbon, and double bonded to another carbon. But you see, in this case, you can have 1, 2, 3, and a 4th bond here to a hydrogen. Here you can have a 4th bond to a hydrogen. Here you can have a 4th bond to a hydrogen. Here you can have a 4th bond to hydrogen. But like I said, not all of them you're going to be able to do that with. This, for instance, right here, you have this carbon is 1, 2, 3, 4 bonds. 2 bonds here, 1 bond here, 1 bond here. Same thing with this one, but these only have 1, 2, 3, 1, 2, 3, and therefore that's why they could have that extra bond. And you assume it's hydrogen if it's not already written out. So something different with this one is completely different, because then you can have double. This one is similar to dichlorobenzene here, but the menthol, if you see here, you see that there are no double bonds going around here. So in this particular case, you can have, here's a hydrogen from here and another hydrogen here and here, because then that's 1, 2, 3, 4, 1, 2, 3, 4 on that. This is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then here 1, 2, 3, 4. So you see that those hydrogens can come out of there. Okay. Now, once you're able to figure out hydrogens and carbons, you're on your way there. We have to figure out next then how are we going to figure out the polarity. We were talking out in first semester that polarity is determined a lot by how many hydrocarbons there are versus how many oxygens and nitrogens and other things that are out there. And we know the importance of understanding polarity in terms of how well it binds to receptors and enzymes, but also how it gets across membranes like the blood-brain barrier and gets then into the brain. So we know why that's important, but let's look a little bit more closely at how we determine polarity. We're going to do it very simply based on, let's go to, alright, we're going to base on something very simple. Alright, what we're doing is looking at just 2 atoms that are bound together. So if we look at this chart up here, we'll see that the fluorine has got the highest electronegativity, and the hydrogen has the the potassium has the least electronegativity. What is that? Well, you already read it. Electronegativities has to do with how well it attracts an electron to itself. So things like fluorine, bromine, chlorine tend to be on the right side of the periodic table, and that's why they have and oxygen have high electronegativities, which means they are really good at attracting electrons because they're close to the right side, and therefore they have more valence electrons, if you recollect from sophomore year, and as a result they're going to be more stable as they get those electrons to then have a full octet or 8 in their valence shell, and therefore these tend to really want to rip electrons away from poor little metals like potassium, which is on the left side, and that's why this has a very weak electronegativity of only 0.8. Determining polarity doesn't have to do with the electronegativity. It has to do with the difference in the electronegativity. So we'll see that the difference between 2 atoms that are bonded together will determine its polarity. So the greater the difference, the greater the polarity. So obviously if we pair up something like oxygen and oxygen, which is O2, you're very familiar with, you'll see that oxygen has an electronegativity of 0.35. That's how much it wants to pull an electron to itself. The other oxygen has 3.5. What's the difference? Well, the difference is 0, and therefore this one has no polarity. Whereas if you were to pair up oxygen with hydrogen, that's a whole different ballgame, because then you have 3.5 here, and hydrogen according to the table is 2.1. The difference here is 1.4. And so we definitely see that there is some sort of polarity there. This oxygen, that's why oxygen tends to be negative while hydrogen tends to be positive when they're paired up, because oxygen is very much better at getting the electron toward itself, and electrons of course are charged negatively. Well, if we take something like carbon and hydrogen, that's a little different, because carbon is 2.5 and hydrogen is 2.1. Is there a difference? Yes, 0.4. The difference is not nearly as much. So carbon tends to be a little bit more positive, hydrogen tends to be carbon is a little negative when it's paired with hydrogen, which is a little positive. So there is 0.4. So how do we know which is polar and nonpolar? Well, anything, as it says right here, when the electronegativity difference is greater than 0.4, like in this case, we consider that to be polar. When it's 0.4 or less, we consider that to be nonpolar. But think about it, even if it's 0.41, it's polar. So it's really kind of a little arbitrary, it's along a spectrum. But this is just barely nonpolar. This, of course, is very nonpolar. And so what we do is what we want to do on these first 5 compounds that we choose here, we're basically going to be looking at polarity. So I would go ahead and circle this one here and go, okay, well, what's the relationship between Br and this carbon that's right here? Well, C carbon is 2.5, bromine is 2.8, and I see that the electronegativity difference here is only 0.3. That's less than 0.4, and therefore I consider that to be nonpolar. Just put an N for nonpolar. All right. However, if I look at oxygen, hydrogen, we already know, circling these two, that one is 3.5 and the other one's 2.1, and therefore the difference is 1.4, and therefore we know this is polar. If we take carbon and chlorine right here, we see the carbon is once again 2.5, chlorine is 3.0, the difference is 0.5, and that's still considered to be polar, barely, but it's still considered to be polar. And so basically what you're going to do is that all the time. Don't worry about the hydrocarbons. The only ones you really need to look at in this case are this one, which would be the same, this one, which would be the same as the other Br combination, and that's pretty much it for those. Now if you're going to go further down, these, then the ones that you're going to be looking at here are the O and the H, O and the H, but also the C and the O, the C and the O here, and they would be the same numbers, and you can, if you figure out one, you can figure out the rest. This one is a little tricky because you have to actually draw it out to make out 2 H's, so we just scratch this one out, and then determine what this is, determine what this is, and determine what this is, because this of course is a carbon. Same thing here, determine this one, determine this to that carbon, which would be the same, and do the same thing here. You have an H and you have an H, determine nitrogen and the carbon, nitrogen and hydrogen, nitrogen and hydrogen. Oh, sorry, I missed this one here. So that's all you really got to do for polarity. Once you get past polarity, then you want to go into functional groups, and that I'll explain later.